All right, Matsu, here we go. We got lesson 3.1.5, part 2, expected value. This is take 3 because people keep on knocking on my door, and then on the last take, I screwed up. Anyways, moving on. Double spin is a game where you spin the spinner twice, and if you get the same amount each time, then you win the amount of money that you spun twice. Okay, so we're going to have two separate events here. Event number 1 is spinning the spinner once. Event number 2 is spinning the spinner the second time. Now we have to look at the spinner and find out our probabilities of each of these outcomes. So on one spin, the outcome of getting a 10 is 1/4 because this is 90 degrees out of 360, which comes out to 1/4 of the spinner. This is the same. This is 90 degrees out of 360, which is 1/4. Doesn't say here on my paper, but this section here is 45 degrees, and 45 over 360 ends up being 1/8. That means this last section here has to end up being 3/8. Why does it have to be 3/8? Because 1/8 and 3/8 makes 1/2, and that's half of my circle. Now all these together add up to 100%. All right, so now we're ready to do an area model for our outcomes of two spins. So we've got two separate spins as our outcomes. So we're going to have combinations of two spins to put in here. All right, let's not screw it up this time. All right, I need 3 lines in here. So if I put one down the middle, and then I cut this one in half. This is much better than the last time I did it. Last time I did it, it just looked gnarly. It wasn't nice at all. All right, gonna go right down the middle on this one. And then cut these in half. I kind of screwed it up, but this is good enough. All right, I'm semi-happy with my area model there. All right, so here's my first event, spin number 1. Spin number 1 has 4 outcomes. I could get $100, I could get $1, I could get $10, and I could get $5. There's my first spin. Then I've got, oops, I hit that thing. Spin number 2. It's my second event. Again, I can get the same amounts, $100, $1, $10, or that looked like a 20, or $5. All right, let's look at our probabilities for each of these. We said $100 was a 1/8 chance, $1 was a 3/8 chance, $10 was 1/4, and $5 was 1/4. Same thing for the second spin. The probabilities don't change on the second spin. This is going to be 1/8. This will be 3/8, 1/4, and 1/4. Okay, so since these are two separate events and we want to see where they are going to occur at the same time, we multiply the probabilities. So 1/8 times 1/8 ends up being 1/64. 1/8 times 3/8 becomes 3/64 because we just do 3 times 1, 8 times 8. So 3/64. 1/8 times 1/4 is 1/32. But I'm going to do something different here. Since I know all these other ones are in 64ths, sometimes I like to add up my probabilities. And if they all have the same denominator when they're fractions, it makes it a little bit easier to do that. So 1/32 is the same thing as 2/64. Oops, 64ths. When dealing with fractions, it's easier to compare things if they have the same denominator. All right, so this one is going to be the exact same as that one. It's 1/32 or 2/64. Next one, 3/8 times 1/8. We've already done that right here. It's 3/64. 3/8 times 3/8 is 9/64. 3/8 times 1/4 ends up being 3/32, which is 6/64. And same thing for this one, 3/32 or 6/64. Over here, 1/8 times 1/4, we've already done that. 1/8 times 1/4 we said was 1/32, which is 2/64. This is also 1/8 times 1/4, so that's 1/32, or 2/64. 3/8 times 1/4, we've already done that. 3/8 times 1/4 was 6/64. No. 3/8 times 1/4 is 3/32, which is 6/64. And this is going to give us the same value here. It's still 3/8 times 1/4. This one right here, 1/4 times 1/4 is 1/16. That's a new number. And in 64ths, this would be 4/64 because I'm multiplying the top and bottom by 4. 1/4 times 1/4, again, that's 1/16 or 4/64. And then 1/4 times 1/4, same, 4/64 again. And our last one is still 4/64. All right, so where do we win on this game? We win, according to this, if we do the same number twice. So I win $100 here. I win $1 9 out of 64 times. I win $10 4 out of 64 times. And I win $5 4 out of 64 times. So what is the expected value of when we play? Now, normally what we would do is we take all 16 of these outcomes, these final outcomes here, and then multiply it by the amount of money that we would have won, or the amount that, the value that we would win in this case. Well, I can ignore everything but the green ones. All these other ones come out as 0 because I don't win that. I only win when I get the same amount. So I'm only going to do 1/64 times 100 plus 9/64 times 1. So 9/64 of the time I'll win $1. 1/16 of the time I will win $10 here. And 1/16 of the time, I'm going to win $5. So here, this is 100 over 64, because you just multiply going straight across. So I'm going to get my answer 100 divided by 64. It comes out to 1.5625. Since this is money, I'm going to go ahead and round these numbers. I'm just going to say this is 1.56. Now 9/64 times 1 is 9 over 64, so 9 divided by 64. That's going to net me 14 cents. 1/16 of the time, I'm getting $10. So 10 divided by 16 ends up being, I'm going to round that to 63 cents. 0.63, sorry. And then this is 5 over 16, so it should be half of that. 5 divided by 16, it's 0.3125. I'm going to round that to 0.31. All right, this is my expected value. We only have 4 outcomes where we win. So we take the probability of it happening times the amount that we win. So this should give me my outcome. All these other outcomes were 0, so I don't have to actually calculate them. Only the green ones give us numbers for our outcomes. So if I take 1.56 plus 0.14 plus 0.63 plus 0.31, I end up with $2.64. So that's how much I should expect to win on one spin. Now, $2.64 doesn't actually show up over here. And a lot of times with your expected values, you're not going to get the exact amount over here anywhere. This is just saying that on an average spin, we would get 264. There is no 264, but if I would spin this 100 times, I could take 100 times 2.64 and find out, oh, I should be making $264. Now that would be possible with these values here. So this is just what I should be predicting to get. Well, a lot of times our predictions don't make actual sense on the spinners, but it kind of gives us a gauge on what the value of playing this game is in the first place. Just a second, somebody's knocking on my door again. All right, sorry, they're delivering my breakfast, and they forgot my coffee, so somebody's going to knock on my door again. Anyways, let's move on. All right, if the game costs $3 to play, will you break even in the end? No. If I'm spending $3 to play it and only expect to make $2.64, I'm probably going to be losing money on this one. So no, we won't break even. Now, is it possible to make more money than what we spend? Yes, of course. I could spend $3 and spin $100 and then spin $100 the second time. And off of $3, I could make $100. So I net $97. That's possible. But according to the probabilities, if I keep on playing this game, I'm not going to come out as a winner in the end because I should expect to only make $2.64. Is this game fair? No, it's not fair because what it costs to play is not equal to what I expect to get out of it. This is how most casinos set up all their games. They usually set up their games so they have a small chance of winning. That way they keep you playing. But they know if they get thousands of people to play, the probabilities are always on their side. You know, if you're spending $3 and they're only paying out $2.64. Now, some people make money, but when a lot of people do it based on the probabilities, they end up winning every single time. All right. Recall the 1-and-1 free throw example. So this is from a while back. 1-and-1 free throw means that if you make the first shot, then you get a second shot. If you miss the first shot, you don't get a second shot. And we talked about this back when we did it, that maybe an area model isn't the best method for doing it. Because when you do an area model in these situations, you get, so this is make it, not make it, not make it. So what happens when you have your sample space with an area model on this one is if you make the first shot, yes, you would get a second shot. If you make the first shot, then the second shot, you might miss it. So that's a possible outcome. But if you miss the first shot, you would never get a second shot. So it doesn't really make sense because on a miss, there isn't a second shot. But the area model would show a probability for these impossible situations. So on this one, I think that the what's it called? The tree diagram is probably the best method for displaying our outcomes. So in the tree diagram, we would do the first shot here, and there's two things that can happen from our first shot. We can make it, or we could miss it. So that's the first shot. We know that she has a 60% free throw average. That's 6 over 100, or we could write that as 6 over 10, which is 3 over 5. So she's got a 3 in 5 chance of making that one. So 3 over 5 is the chance of making. So that means she's a 2 over 5 chance of not making that shot. Okay, so if she makes the shot with a 1-and-1 free throw example, that means she will get a second shot. And the second shot, she can either make or miss. Now the second shot, since her free throw average is 60%, it's going to have the same probabilities. Making it would be 3/5 of the time. Missing it would be 2/5 of the time. So since these are two separate events, two separate shots, we would multiply the probabilities to see what the outcomes are. So making it and then making it again. 3/5 times 3/5, that would be 9/25. Making it, then missing it, that would be 6/25. And then over here we got an interesting one. Missing it, well that's it. She just missed it. And she doesn't get a second shot. So there's actually only 3 outcomes here. Making it twice, making then missing, or just missing the first one and not getting a second shot. So a tree diagram only has 3 outcomes in our sample space, and that's more correct for a situation. Whereas if we would have done an area model, we would have shown 4 outcomes, but really one of these outcomes down here doesn't make sense because she doesn't get a second shot if she misses the first one. So tree diagram makes more sense in this situation. Now if I did this as percentages, 2 out of 20 would be or 2 out of 5 would be a 40% chance. 9/25 ends up being a 36% chance. And 6 out of 25 ends up being a 24% chance. Now you see that if we add these up, 36 plus 24 is 60, plus 40 is 100. So we're getting a 100% chance. All of our outcomes should eventually come out to 100%. What is more likely? Scoring no points or scoring some points? Well, it's more likely that she's going to score some points. Because in this situation, she scores 2 points, 36% of the time. In this one, she makes then misses, so she scores 1 point. In this situation, she just misses 0 points. The pen's dying. All right, so what is the expected value of Delilah in the 1-and-1 free throw example? Well, she has a 36% chance of getting 2 points. So this would be 2 points times the probability, 36%, 0.36. And then she can get 1 point 24% of the time, 0.24. Now this one, we're not going to get a number from because this is 0 times 0.4, which is 0. So we're only going to get expected values from these two, or numbers for our expected value from those two. So 2 times, I don't know why I'm using a calculator, I already know what the answer is. 2 times 0.36 is 0.72. 1 times 0.24 is 0.24. And 0 times 0.4 is 0. So our expected value for that is 0.72 plus 0.24, which would be 0.96. So she should expect a little bit less than 1 point each time that she takes a free throw or takes a 1-and-1 free throw situation. Can that actually happen? No. But this is, if you do the experiment over several times, this is what you would want it to come out to. Kind of like, it's almost like an average. It's not really, but it's like an average. Let's just say average. It sounds good. All right, next page. All right, Janine's teacher gives her an opportunity to raise her grade. She's given a special die, and if she gets a positive number on the die, then her grade goes up. But if she rolls a negative number, then the grade goes down. The grade goes down? Question mark? I don't think that's a question. The diagram shows all the sides of the die. So this is kind of like the die's been spread out. You know, this is like a, what do you call those, nets? A net of it. Like you could make this into a die. So this teacher is big into gambling, I guess, because they want their students to gamble with their grades. So it looks like she wins 2 more points for the grade here, here, and here, 1 point for the grade. But if she rolls these, she loses points from her grade. Oh, this is gambling. So since this is a 6-sided die, each side of the die should have a 1/6 possibility of occurring. So just a second, my coffee's here. Oh, this video is taking forever, but I got coffee now, so everything's cool. All right, so what are the qualities of a fair game? So the qualities of a fair game is that the possibilities of winning and losing should come out as equal possibilities. So we have an equal chance of winning and losing. And in expected value problems, we would expect the expected value to be 0, because that's an equal chance of winning and losing. So what is the expected value of a fair game? It should be 0, because that means you have an equal chance of winning or losing. So what is the expected value of one roll of the dice, and is it fair? So are we going to get 0 or not? So 1/6 of the time, we're going to get 2. 1/6 of the time, we're going to get 2. 1/6 of the time, we're also going to get 2. And another 6 of the time, we're going to get 1. 2 more. 1/6 of the time, we get -4. And 1/6 of the time, we're going to get another -4. Let's look at these outcomes. 2 times 1/6 is 2/6. I'm just going to leave it as 6 for right now. 2/6 again. 2/6 again. 1/6. -4/6. And -4/6. So since everything's in 6, I can just add up my numerators. 1, 2, 3, 4, 5, 6, 7. -8. Oh, this teacher is evil. The teacher has set up this game so that if they roll the dice, they're going to lose on average. We have a negative expected value. So if these kids roll their dice, more times than not, they're going to lose points and not get extra credit. That is an evil, evil teacher. No, this is not fair. I should do this sometime. It's pretty interesting. All right, so no, this is not fair. A fair game would have 0 as our expected value. How could you change one side of the die to make it fair? We need 1 more 6. So maybe if I made this into a 2 instead of a 1, this would be 2/6, and then it would be a fair game. So if I change this one to a 2, this number here would have been 2/6, and then I'd have 8/6 minus 8/6, and then it would have been a fair game. So change the 1 to a 2. Find the expected value if region A is 7 degrees. Ooh, 7 degrees. Well, 7 degrees is 7 out of 360. And so the value for that one, we would get $100 or 100, whatever points it is. Now the rest of the regions should be 353 degrees out of 360. And then we multiply by 2 for that one. So 7 out of 360 times, I would expect to get 100. And 353 out of 360 times, I expect to get 2. So let's see what that's going to come out as. Why is my calculator not working? There it goes. So 700 divided by 360. These are not nice numbers. This is we're just going to call it 1.94. It's 1.94 repeating, but whatever. And then for this one, I would do 353 times 2 divided by 360. Comes out to 1.961 repeating. We'll just call it 1.96. So 1.96 plus 1.94 ends up being 3.9. So that is my expected value, 3.9. Now it's somewhere in between these two numbers, which would make sense because I can't get an expected value below 2 because I'm always going to get at least 2. So your expected values should be between the two numbers that are your possibilities. Last part, find the value of x so that the expected value of one spin is 3. Well, that's kind of mean. So this is 1/4, this is 3/4. So this would be 3/4 times 2 plus 1/4 times x is equal to 3. So this is 6/4 plus x over 4 equals 3. I would go ahead and clear the fractions on this one. Multiply everything by 4. That gets rid of my fractions, and I end up with 6 plus x equals 12. Subtract 6 from both sides, and x would be 6. That was beautiful. For this one, if this is 60 and this is 60, 60 out of 360 is 1/6. So this is 1/6, 1/6. So this must be 4/6 over here. So for this one, I would say 1/6 times -3 plus 1/6 times 1 plus 4/6 times x equals 3. So this would be -3 over 6, 1 over 6, and 4x over 6 equals 3. So now all I have to do is clear the fraction and multiply everything by 6, which is delicious. So I get -3 plus 1 plus 4x equals 18. So this is 4x minus 2 equals 18, combining my two like terms here. And then I add 2 to both sides and get 4x is equal to 20. Divide by 4, and we get x is 5. Yay, math! All right, we finished it. I get to eat my breakfast. See you later. Bye-bye.